Next, we are going to look at primitive roots. And so here's a definition that we kind of want in our back pocket before we dive into primitive roots. And so here, p is prime, a and k are integers. When we talk about the order of a, and a is an element, and of a mod p is the smallest exponent such that a to the k is congruent to 1 mod p. And so this definition is a little abstract. We will do an example in a moment, but I want one more proposition before we do that, and here it is. For p a prime and a an integer, p does not divide a, we suppose that if we take the nth power of a, that's congruent to 1 mod p, and then we say that the order of a mod p is n. Okay, now here you might need to pause the video, try some numbers, and play around with this and see what happens. I'm not going to prove the proposition. It is proved in the textbook, so feel free to refer to that as needed. It's called a theorem in the textbook, so it's theorem because they prove it. Proposition because I'm proposing it as an idea without doing a formal proof. Okay, so here's our example. If I think of p as 5 and a as 4, okay, I want to find k, right? Alright, if I look at, so p is 5, so I'm in a finite field of 5 elements, right? And I'm looking at 4. So then I'm looking at 4 to the first, that's 4, and then, or congruent to 4, I'll just add that. And then 4 to the second is congruent to, so that'd be 16 in a field of 5 elements. That's actually congruent to 1. Okay, and so now we would say that the order, so here that's the first thing that happened. So the order of 4 mod 5 is 2. Okay, and now here, and so that's the definition. Okay, for the proposition, suppose that a to the n is congruent to 1 mod p. Okay, so now n, if we keep going, okay, we might say, well, maybe we want to do, like, Fermat's Little theorem is stuck on our brain, so we're just going to continue doing this. 4 to the third, which should be congruent to 4, and then 4 to the fourth is congruent to 1. Okay, now this area of circle, and I'll do it in a box. Okay, this box, that's what Fermat's Little theorem would say, right? We do a to the p minus 1 is congruent to 1. Okay, and that's certainly true, right? P does not divide a, that's all fine. So Fermat's Little theorem would say, yeah, we do 4 to the fourth and it's congruent to 1, but that does not mean there isn't an earlier power on an element that doesn't produce, or that produces 1. It does happen with 4. And that's where this proposition comes into play. So even though n here would be 4, according to Fermat's Little theorem, right, the order of a mod p is 2, and so we're saying that 2 divides 4. Yeah, duh. We learned that in, like, 3rd grade. Okay, so anyway, that's just kind of illustrating the definition of order and this proposition. Okay, now the next question is, what if n is equal to k? Okay, so now what if the smallest number here was actually indeed this? Well, I think we've seen this a few different times, and so that's where this primitive root theorem comes into play. All right, so we have p a prime number, then there exists an element in fp star, and so again, this is we talk about this as the group of units in fp. You might also call it the multiplicative group, or in this case, a multiplicative field. And then if we look at, or if we find this element G, if we take powers of it, it generates the entire group of units. and then we talk about these as primitive roots or generators. And yes, you may recognize this language from a previous group work. And so all elements of this, or all elements that satisfy this condition, or the primitive roots or generators, they have order p minus 1. Okay, so this is a situation where that n from above is equal to k. And then so just as a quick example, if we look at in F5 star, which is just 1 through 4, if we look at 2, we get, well, 2 to the first is going to be congruent to 2. If we look at 2 to the second, that would be congruent to 4. 2 to the third is congruent to 3. And then 2 to the fourth is congruent to 1. So then 2 is a generator for F5 star. Okay, so that's the idea with primitive roots, and we'll get some practice with this in homework and in group work.